Good morning. Today we're going to begin Unit 4, and we're going to discuss the meaning of the derivative in context, as well as we're going to talk about some rates of change in their units. So in Units 2 and 3, the focus was mainly how to take the derivative, right? All the rules and skills that are involved. But Unit 4, we're actually going to apply it to certain scenarios or situations, okay? So what we want to talk about real quick is in this blue box of just what does it mean to have the derivative, right? What is the meaning of f prime of a? And I want you guys to just kind of recall that f prime of a is the instantaneous rate of change at x equals a. Okay, another fancy, a less, book word for instantaneous rate of change is slope, right? I'm finding the slope at a point, okay? And I have a few inequality statements below. If I were to say that the derivative is greater than 0, what conclusions can you draw? Well, I know if the derivative is greater than 0, I know that the slope is positive. And a better way to say than the slope is positive, I can say f of x is increasing. Okay, if you have a positive slope, you know your function is going up. Okay, it's increasing. Now, if f prime of x is negative, then you know your slope is negative. And in other words, just like before, we know f of x is decreasing. Okay? And then last but not least, if f prime of x is equal to 0, that means that the slope is 0 or my function is constant, right? So I'm going to say the slope is 0. It's a constant function. And otherwise, I could say f of x is constant. Okay? So those just kind of some little meanings. So I'm going to refer back to those throughout the lesson in terms of context. Okay? Now, I give you a scenario for example 1, all right? And I want to kind of understand some meanings of notation. So a file is downloaded to a computer at a rate modeled by m of t, okay, where t is measured in seconds. It's important, okay? And m of t is measured in megabytes per second, okay? So interpret the meaning of m of 3 equals 24. Well, I know at t equals 3 seconds, okay? Get my pen working here. Sorry about that, guys. The computer is downloading at a rate of 24 megabits per second. Okay, so again, we have to use the units in the question. Now, here's the part that you might be a little less familiar with. What is the meaning of m prime of 3? If I tell you m prime of 3 equals 13.5, I can say at t equals 3 seconds, the rate of change is increasing by 13.5 megabits. Oh, that doesn't look like megabits. Let me rewrite that. Per second squared. Okay, so if you have the first m of t is megabits, the derivative will be megabits per squared. Now, so on, if I were to take the second derivative, I know t is 3 seconds. And the 0.2 is referring to megabits per second cubed. Every time we take a derivative, we're finding our new rate of change. So we're finding how the function before it changes over time. So if you did megabits per second squared over time again, that's now going to give you megabits per second cubed. Now, if you have this one down here at t equals 3 seconds, we're going to have a negative 0.3 megabits per second to the fourth. Okay, those would be the units on my answer. So that's important. Okay, now normally I'd write a complete sentence, but I want the focus to be more on the units for right now. So in this problem, the original function gave me a rate of change, which is different, but it can happen. So the original function was megabits per second. So then the derivative would have been megabits per second squared. The second derivative would have then been the next step down, which would have been megabits per second cubed. And then lastly, megabits per second to the fourth, right? So every time you take the derivative, you're going to divide by another unit of time, or another unit of the input. In this case, it's time. Okay, so let's do another one. So Joey Chestnut begins the annual Nathan's hot dog eating competition on July 4th. The number of hot dogs that Joey Chestnut eats can be modeled by h of t, where t is measured in seconds. All right. So if I have h of 10 equals 8, then I can say at 10 seconds, Joey Chestnut has eaten 8 hot dogs. Okay. So it's just the input and output of the function. Okay. Now, if you take a look at h prime of t equals 1.5, I would say that we'll say at time at t equals 10 seconds, Joey Chestnut is increasing his hot dog consumption by 1.5 hot dogs per second. Okay, so he's starting to eat faster, right? His rate of change, his velocity of eating hot dogs is increasing, right? So the amount is increasing by a rate of 1.5 hot dogs. Now, as he gets more full, you know that rate of change will probably go negative. It'll probably start decreasing. But again, I want you to kind of understand in context here. All right. The number of mistakes that Mr. Delamorte makes in his math packets is modeled by M of P, where P is the number of packets he's completed so far this year. Okay, so what's M prime of 15 equal to in this context? Well, if M of P, okay, is going to be the where P is the number of packets he's completed this year, and M of P is the number of mistakes. So I would say after completing 15 packets, Mr. Delamorte makes mistakes at a rate of 2 mistakes per packet. Okay, so again, it's a rate of change. Okay, now the following problems are calculator active, and they're actually from old AP exams. So I want you to kind of see what this looks like in context for an AP problem. All right, so I have my calculator to the side here. I'm going to utilize it as much as I can. It says the wind chill is the temperature in degrees Fahrenheit a human feels based on the air temperature in degrees Fahrenheit, and the wind velocity v in miles per hour. If the air temperature is 32 degrees, then the wind chill is given by the following function. Okay. Find W prime of 25. Using correct units, explain the meaning of W prime of 20 in terms of wind chill. So, ladies and gentlemen, I'm going to use my calculator here. If you hit math number 8, we can have this calculator do the derivative for us. So 55.6 minus 22.1, I'm going to use x instead of v, raised to the 0.16 power. And I want that derivative when x is 20. Okay, so you can see how I typed it in. So I'm going to write, the very first thing that I'm going to write is W prime of 20 equals a negative 0.285. We're just going to terminate that decimal at 3 decimal places. You don't need to round it. Okay, now we need to actually use correct units and explain the meaning. So in this case, V stands for the wind velocity. So when the wind velocity is 20 miles per hour, the wind chill is decreasing at a rate of 0.285 degrees Fahrenheit. Ooh, let me write that degrees Fahrenheit a little better. Per unit of V, right? So per miles per hour, right? Because V is measured in the wind velocity. Okay, so wind chill was measured in degrees Fahrenheit. V was measured in was wind velocity in miles per hour. So then the rate of change would be degrees Fahrenheit per mile per hour. Okay. All right, let's keep going. Okay, so now this is a 4-part question. Now we only know the content for 2 of the parts. They only apply to what we've learned so far, but we'll add on. We'll go through all of them. So this one was from 2001. Okay, it says it also graphing calculator active. It says the temperature in degrees Celsius of water in a pond is a differentiable function W of time t. Table to the right, in this case above, shows the water temperature as recorded every 3 days over a 15-day period. Use the data in the table to approximate W prime of 12. You can see and then show the computations that lead to your answer. Interpret the meaning of the derivative in part A in the context of the problem. So if the best I can do to approximate W prime of 12 is going to be to find the average rate of change for the values around it. Okay, so W of 15 is going to be 21. W of 9 is going to be 24 all over 15 minus 9. So I get a negative 3 over 6, or in this case, a negative 0.5. Okay. Now, we need to show computation and we need to interpret the meaning here. All right. So this is going to be a change in temperature, so degrees Celsius per day. Okay. So I can say that the WT is, I want to make sure I get my units right. The temperature of the pond is decreasing by a rate of 0.5 degrees Celsius per day on day 12. Okay? And maybe I should use the word approximately right? Because we're doing an approximation here, is approximately decreasing at a rate of 0.5 degrees Celsius per day, okay? Again, the focus is on the units here. So it says a student proposes the function P given by the following as a model for the temperature of the water at time t, where T is measured in days and P of T is measured in degrees Celsius. Find P prime of 12 using appropriate units. Explain the meaning of your answer in terms of water temperature. So it's kind of the same idea, but we have a calculator here, right? So I'm going to use that calculator. I'm going to say, I'm going to take the derivative of, I'm going to use x's, 20 plus 10 x times e to the negative x divided by 3 power. And I want to know that derivative when p is 12. Okay, so it says find p of 12. So I'm going to start with that answer first. P prime of 12 is equal to a negative 0.549. I'm just going to terminate after 3 decimal places. And then explain the meaning. The pond is decreasing in temperature at a rate of 0.549 degrees Celsius per day, right? And I should say on day 12, right? So I have when it's going to happen and what the rate of change is with the correct unit, okay? All right, example 6. So on a certain workday, the rate in tons per hour of unprocessed gravel arrives at a gravel processing plant is modeled by this function, okay, where T is measured in hours, 0 to 8. Okay, so I have gravel arriving to this processing plant, okay? At the beginning of the workday, T equals 0, the plant has 500 tons of unprocessed gravel. During the hours of operation, 0 to 8, the plant processed gravel at a constant rate of 100 tons per hour. So part A, find G prime of 5. Now again, this was a calculator active problem. So I'm going to say math number 8. So I'm going to say I have a 90 plus 45 cosine. I'm going to use my fraction of x squared over 18. And I want that derivative at 5. Now, before I press enter, one thing you should know, you should always be in radians in this class. So whenever you're typing trig functions in your calculator, we want to make sure we're in radians. So G prime of 5 is equal to a negative 24.587. And then I can say when T equals 5, and what's our unit of time here? Hours. The amount of gravel, we can say unprocessed gravel, is decreasing at a rate of 24.587. Now I need to make sure I have correct units here. So gravel is being brought in tons, right? It says tons per hour. Okay. The rate in which tons per hour, so it might actually be tons per hour squared. Okay, so it says G of T. So if you read that first sentence again, the rate in tons per hour at which unprocessed gravel arrives at a processing plant is modeled by this. So if G of t is already in tons per hour, if you take the derivative of it, it's now going to be in tons per hour squared. It would be the next unit. Okay. All right. Part C. The amount of unprocessed gravel at the plant is increasing or decreasing at t equals 5. Show the work that leads to your answer. Well, I know that we're processing it at G of t, right? So G of t is the rate in which we're processing it, or that's the rate in which it arrives. And then I also know that during the operations, the plant processed the gravel at 100 tons per hour. So it's arriving at a rate of G of t, but then I am removing it, I'm processing it at a rate of 100, okay? So if I were to do this at 5, so I want to know G of 5 minus 100. Not G prime of 5, just G of 5. Okay, because G was already a rate of change. So if I do this, I'm going to say 90 plus 45 cosine, get my fraction going here, t squared would be 25 over 18. I'm using the function, by the way. And I plugged 5 into that function. And this gives me 98.14 minus 100. And if you subtract 100 from that, I have a negative 1.859. So what I can say here is I can say that it's decreasing at t equals 5 hours because G of t minus 100 is less than 0, right? So the rate of change in which it's arriving minus the rate of change in which it's leaving, right, is negative. So I know more is leaving, right? So ultimately, I know it's going to decrease. Okay, so these were just some examples kind of put into play. These are also examples of questions that I can put on any of my assessments. So if you have any questions, please contact me, let me know, and we can discuss further.